Okay, guys. Once again, I welcome you all. Okay, and a very good morning to all of you. Today is the lecture number 10. Okay, lecture number 10, which is based on the abrasive jet machining. So far, up to lecture number 9, from past 4 lectures, we were discussing about the EDM process, that is electric discharge machining. Before that, we were discussing about the ECM, and before that, we started with the chemical machining operations. Okay, so three advanced machining process we have covered. Okay, so and one more thing, if we talk about the chemical machining operation, ECM and EDM operations, then these were the operations which were based on basically the chemical energy or the electrical energy that we are using. But this process, which is a abrasive jet machining process, this process is like a mechanical process. Okay, but as I discussed in the very first day in the introduction part, that we are calling it as a non-conventional machining processes. So because in conventional machining there is a contact between the workpiece and the tool. Okay, but in these processes there is no contact between the workpiece and the tool. All the operations. So abrasive jet machining here is here is also there is no direct contact, but whatever the abrasive particles are there, they are impinging over the workpiece surface and removing the material. Okay, guys, so here basically we are using this process. This abrasive jet machining process is based on that conversion of pressure energy into the kinetic energy. Okay, so from that we will start. And as I already mentioned that these are the advanced machining processes. So we will go step by step in the processes. Like first we will discuss about the principal part, that what is the principle. Then we will discuss the working. Then we'll discuss about the material emolment, which is a very important criteria for all the machining operations. And then we'll go for the numerical problems, if any available. Okay, so let's start with the principal part. Okay, so the principle is as I said, that we are using the pressure energy is to convert it into the kinetic energy. Now, just I am first of all, I just want to tell you that what the meaning of this process is. Like AJM basically, where A represent the abrasives or abrasive particles, we can say. Okay, and the J is represent the jet. Okay, so this jet is, and M is machining. So abrasive particles, which is jet, means what? Very high velocity. We are using the very high velocity, whether any fluid, like whether it's a liquid or the gas is there. Okay, so if it is a liquid, then we are there is a separate operation for that, that is abrasive water jet machining. But here, like, we are using this jet of air only, air or any gases. So please keep in mind that any air or any gas we are using. I will discuss these, what the gases are available or we are using that. But this gas jet will be formed of the air and the gas. Now, why we are calling it as a jet? Because it has a very high velocity. Okay, because generally the aeroplanes, like, we are not calling them as a jet, but jet is a different category of aeroplanes. Okay, why we are calling it as a jet? Reason is it is flying with a very high velocity. Okay, so jet meaning the very high velocity, and here we are calling it as we are using the abrasive jet machining, not abrasive water jet machining. So that jet of this air or the gas uh, that we are using. Okay, that we are using to remove the material. Okay, now abrasive particles, now we are using the combination of these two, or we can say like abrasive slurry. But abrasive slurry, sometimes students should confuse that abrasive slurry means there is only the abrasive particles is there and the water is there. Okay, so it's not like that. Abrasive slurry means the abrasive particle is there plus fluid is there. So fluid can be anything, like it can be a liquid or it can be a gas. Okay, so here I'm talking about, if I'm talking about the abrasive slurry, then it means that here I'm using gas along with the abrasive particles. So these two combinations we are using to remove all of the material. Now, as I said, that the pressure energy is converted into the kinetic energy. Okay, and let's see, let's discuss this one. Okay, so this is basically this portion is basically the nozzle. This portion is basically the nozzle, okay, and this is the workpiece. Okay, guys. Now, okay, so next is like this is the blue color is basically, this blue is basically the boundary of this one. So this is basically the nozzle, and here, like guys, you can see that this black color is boundary is also there. Okay, so this black color boundary. So this is nothing but like we can say this boundary is basically the adjustable boundaries. Adjustable boundaries. Okay, now adjustable boundaries means that like it's like that this is a nozzle. Okay, this is a nozzle, and if you want to increase the diameter, or if you want yeah, if you want to increase this diameter, like maximum, this is the diameter can be attained by a nozzle. Okay, maximum diameter is this. Like minimum, if you want to move, if you want to reduce this diameter, then we can adjust these boundaries towards the center line. Okay, this is the center line. We can move these adjustable boundaries towards the center line. So this diameter at this portion, this is decreases and it can be increases. Now this diameter, the nozzle which we are using generally has the diameter in the range of 0.2 to 0.2 to 0.8 mm or 1 mm we can say. Okay, this is in some of the book like it is 0.2 to 0.8 mm, or in some of the books it's like up to 1 mm. So that there is no big issue, but it should be adjustable. Okay, so now how we can adjust by using these adjustable boundaries. Okay, like this one. So these are the adjustable boundaries. If we have to reduce the diameter, then we can move these adjustable boundaries towards the center line. Or if we want to increase the diameter, then we can move towards the nozzle. Okay, towards the nozzle boundaries, exit boundaries. So we can increase the diameter. Now these black particles are basically this circular shape. This is basically the abrasive particle. This is basically the abrasive particles. Okay, now as I said that gas, we are using the air abrasive particle of the with the jet. Okay, so this jet is formed basically of the air and the gas. So here like it's like when this air will come in contact with the atmosphere, so it will be vanished. Vanished means it is we are using this jet to just provide a high velocity to the abrasive particles. That's it. Okay, when it will come into contact with the atmospheric gases, like it will not be visible to you. Okay, guys, please silent. Adil. Okay, guys. So when this air will be in come with the atmosphere, in come in contact with the atmosphere, so it will be vanished out. Okay, it will not be visible. So here I am just showing only the abrasive particles. But these abrasive particles here, which is moving with a very high velocity and which is above the 150 mm, sorry, meter per second. This very high velocity. Okay, as I mentioned that this jet we are using, and this jet is we are using this velocity greater than the 150 meter per second. So this is a very high velocity, and this, when this abrasive particle is mixed along with this jet, then definitely this abrasive particle will also get a high velocity. Okay, and when this has a very high velocity, it means that kinetic energy will be equals to, which is half mv square. If the velocity is very high, then no doubt the kinetic energy will be very high. Okay, if the kinetic energy will be high, then this abrasive particle is not like just jumping over the, or it's not like it's just falling over the workpiece surface, but it is impinging over the workpiece surface. It's a kind of, it's treating like an impact loading. Okay, because these abrasive particle which is along with the jet of 150 meter per second, they are basically impinging over the workpiece surface, and they are removing the material from the workpiece area. Now here we have to consider that these abrasive particles, here we, one of the assumptions, there are a lot of assumptions, but this is one of them, that these abrasive particles that we are using, that are generally in spherical in nature. That is spherical in nature. Okay, means spherical means diameter of that we are considering that they are the shape of that is spherical, because they are random in shape. Okay, now we can say like spherical we are considering, but it should be like this one. Okay, like this one. So these random boundaries, abrasive boundaries are there. So these are like these are the boundaries through which basically these are the hard abrasives are very generally it has a very high uh, very high strength, because these abrasive are like generally few of the abrasives are basically the Al2O3 alumina, okay, and silicon carbides, and others are also available, so that we are using, and it has a very high strength. So when they are impinging over the workpiece surface, they are basically not only like yeah, they are basically directly removing the material, and it's, as I mentioned, that they are not, it's like falling over the workpiece surface, they are impinging with a very high velocity. So when this shape, this random in shape will come in contact with the workpiece, no doubt it will remove the material from the workpiece area. Okay, so please keep in mind that abrasive particles which is impinging over the workpiece surface, which has a very high velocity, and generally these are in the spherical nature. Okay, so rest of the things we will discuss in the working part if anything is remaining. So first of all, the pressure energy is converted into the kinetic energies. So here one thing is clear, that kinetic energy of this abrasive particle which is impinging over the workpiece surface, so because of that only the material is removed. But still you can ask me, sir, we are unable to understand this pressure energy. So that I will tell you in the working part, guys. Okay, so next is like abrasive particles impinging over the workpiece surface, which is at very high velocity, so that we have already discussed. Okay, guys, so let's move to the working part. So now working is basically here. There are some of the elements. These are the elements that we are using. Okay. So guys, either you can present it in a like you can create a compressor and then dryer, then filter. But I'm just making a boxes only. Okay, just to tell you guys that what these elements are. Okay, and why we are using it. Okay. So first is like we are using the air compressor. So generally, most of you are aware about that air compressor is used to store the gases or air, we can say, at very high pressure. So air or gases we are using. So now like gases is like we can say like CO2 we can use, or N2 we can use. Okay, so these are the gases that we can use at a very high pressure. So pressure is like as compressor meaning is what, we are storing the gases at very high pressure. So pressure is in the range of 2 to 10 bar. Okay, this is very high pressure. So this, at this pressure we are maintaining these gases. Sometimes on behalf like argon also we can use, but generally we are avoiding this argon due to the liquid quantity. Okay, the quantity of liquid is more in that. Okay, so if we are using like, so after that basically after this air compressor at which the air or the gases is stored, after that we are just there we are using the pressure gauges, so we are allowing it to move towards the workpiece side. So after that basically there is a pressure gauge is there, so accordingly the pressure gauge we are maintaining the pressure, as well as we are allowing it to move toward the workpiece side. So then we are using the dryer. Dryer is simple meaning that if it has any, okay, so yeah, like we are using the pressure gauge over here, so which is like just pressure wall we can say, like which is allowing the gases to pass through the workpiece. Then we are using the dryer. So simple meaning like dryer is used if there is any water molecules are there or particles are there, water particles. Then it should be it should not be like water quantity should not move along with that, along with the gas. Only we need a gas here. Okay, and then again we are using the filter. So like generally the size is not matter here, the what size of the bubbles or air particles we are using, but still like in other words like still from the dryer, because we are, by the way, we are using at very high temperature during the dryers, but we are not using in a length. Okay, so whatever the gas which is coming with a very high velocity, it should not be like without any particles. It should move along with that, along past, it's basically past the dryer. Okay, so if there is still any particle is there, then we are using the filter. So filter is like it's just bifurcating the air particles and the water molecules. Okay, so this at the end of this water molecule should be separated. Okay, only air can be passes. Now here like we are using the wall. So after that basically the mixture. So here we are using two systems. First is here the wall we are using, and here also there is another wall. We are calling it as a hopper. Okay, we are calling it as a hopper, and this hopper is basically the we are filling keeping the abrasive slurry, abrasive particles over in this hopper. So there is a wall is there, so through this basically whatever the flow rate or the mass flow rate we have to maintain, or volume flow rate we have to maintain, so we just open the wall accordingly, and this abrasive particle should be uh, um, move to the mixture. Now why we are calling it as a mixture. Now it's very simple that here in this mixer there is a mixing of abrasive particles and the air. Okay, now air which is coming out very high velocity from this side, and the abrasive particle which is passing through this one. So they basically abrasive particle get a very high velocity. Now as they get a very high velocity, they move towards the workpiece side through these hoses. Okay, and then we are using this nozzle. So rest of the part we have already discussed in the principal one, that these abrasive particles, these black one are the abrasive particles which is coming through this very with a very high velocity, and they are impinging over the workpiece surface and the removing the material. So that we have discussed the in the principal part. Now here some of the important parameters that I want to add over here, that this is a nozzle. Okay, this is a nozzle and nozzle exit basically we can say, and this is the workpiece. So is workpiece means the top surface of the workpiece where the abrasive particle will direct come and impinge over the workpiece surface, means that will remove the material. Okay, so if this is like this is the nozzle tip. Okay, this is the nozzle tip and this is the workpiece surface. So this distance we call it as a this distance from here to here, this distance we call it as a standoff distance. Standoff distance. Okay, or in some of the book like it's mentioned like nozzle tip distance. Nozzle tip distance, either SOD, that is standoff distance, and the nozzle tip distance, NTD. Okay, this is like this why we have to discuss it, because this is a very important parameter. Okay, why it is important? Because like this is like just consider that this is the workpiece and this is a nozzle. Okay, so if it is near, then whatever the abrasive particles is coming and impinging over the workpiece surface, it is at very high velocity. Okay, so they will basically the material removal rate should be increases, we can say that how much amount of the material is removing per unit volume, or the abrasive particle which is impinging over the workpiece surface. As we are increasing this distance, okay, as we are increasing this distance, now you can see that is the abrasive particle which is coming out through this nozzle, they will basically try to spread. Okay, is the abrasive particle which is coming through this one, they will basically try to spread, and when they will spread they will move like this. Okay, if they move like this, then definitely this area, whatever the area, this area is increasing and this area is increasing. So this area, when it will impinge over the workpiece surface, that area is increases, means more particle will cover the more area on behalf of this one. Like when this standoff distance was very small, that time whatever the abrasive particles is there, they are if all the abrasive particle were impinging over a small area. So now you can just assume that when more particle is impinging over a small area, they will remove the material very fast. When the more particle will cover more area, the material removal rate is reduced. So we have to keep in mind, that's why this standoff distance is very important parameter. So please keep in mind. Okay guys, next is I forgot one more thing I want to add over here is okay, let's discuss in the parameter. So this is the principal part and this is the working. Okay, these abrasive particle is coming over here and they are impinging over the workpiece surface and they are removing the material. Okay guys, so let's go to the okay, what the other thing is remaining. The important criteria for this abrasive jet machining is the distance between the nozzle and the workpiece, as
हेलो
this
सर
is the yes
सर हमें इसका कितना पैसा रखना पड़ता है सर ताकि वो हमारा नोज
uh, yeah, please ask Rashid again.
हमें सर पैसा कितना रखना पड़ता है सर
pressure I mentioned na Rashid, that 2 to 10 air compression में जो आप pressure रख रहे हैं, that is 2 to 10 bar.
जी सर
Okay,
जी सर
okay, so pressure is basically we are maintaining that pressure into the compressor only, air compressor. That's why we are using the compressor. Simple meaning, wherever you are using, wherever you see the compressors, they basically maintaining the air at very high velocity. Generally, if you will see, like if you have a car or any vehicle, and whenever you are going, nowadays it's like the gas, the tubeless tire is there, so there is there's no whenever this in the tubeless tire also gas is filling, air is filling, okay, in the vehicle. But still when you will go to the any shop for the puncture, okay, then they are having a compressors, okay, and they are basically in the morning basically they are just retaining it, मतलब वो उसको start करते हैं then उसमें air को compress करते हैं, okay, then air is compressed and that is maintaining at very high velocity, sorry, at very high pressure. So when they are opening it, this very high pressured air is coming out from that one and that is filling inside the our tire and tube, we can say, okay. So
Yes, sir.
okay, is it fine?
Okay, sir. Thank you.
Okay, great. So, okay, so important criteria here is two. One is the standoff distance on NTD, we can say nozzle tip distance, and another is the angle of impingement. Yeah, I want to mention that one. Okay, so here is basically here is we are using this nozzle like this. Okay, so what we can do is like if we'll keep this nozzle like this only, then whatever the abrasive particle is coming, they will basically impinge over the workpiece surface in straight motion only. But what happen? Straight motion means we can produce only such kind of shapes. Grooves basically we can produce through that. But if you want to make some curve, or like if you want to make some curve over here, or for an example, if you want to make like this kind of shapes, like dovetails, we can say, if you want to make like this, so for that basically we have to rotate it. So what we are providing here is we can just rotate this nozzle like this, okay, like this. So whatever the abrasive particles now, they are basically have this direction, okay, and this rotation, when we are rotating this one, this angle we are calling it as an angle of impingement. Angle of impingement, and that is in the range of 60 degree to 90 degree. Okay, ज्यादा लेके जाओगे तो उससे क्या होगा, like it would be like some air, this abrasive particle will be go waste, they will basically we cannot keep like this, okay, because workpiece is here, okay, we do not want that this abrasive particle should go waste, okay. So please keep in mind that one. Generally this angle is in the range of 60 to 90 degree, okay. The next one is the abrasive particles impinging over the workpiece remove the material from the workpiece surface due to the micro cutting or brittle fracture in the form of microchips. Guys, this I will discuss in the material removal rate, okay, so no need to worry. By the way, this micro cutting is nothing but the kind of wear mechanism. Wear mechanism means the material, where the material is removed due to the abrasion, so there is a wear mechanism is there, okay, so that is micro cutting here we are using, okay. Next is the abrasive particles used in the form of grit. Okay, here basically whatever the abrasive particle we are using, we are defining that by the grit. Okay, it's not like we are calling it as an abrasive particle. Here we are defining them by the grit, and that is in the size of 50 micron. Generally, it is the range that is 10 to 15 micron. It's not exactly 50 micron. It is in the range that is 10 to 50 microns. Okay, 50. So please keep in mind this one. Let's move to the parameters, guys. After this I will give you the time, so that if you have any doubt you can ask me, okay. And by the time also, like if you like Rashid has asked, so if you have any doubt you can ask. So four important parameters is there. First is the abrasive particles, okay, what types of the abrasive particles we are using. Carrier gas, that what types of carrier gas is available and we can use that. Next is the abrasive jet and the nozzle. Okay, so first let's discuss about this abrasive particles. So abrasive particles, as I said, that alumina you can use, okay, silicon carbide you can use, or the glass beads also you can use, or like dolomite is also available, that dolomite beads are there, so we can also use that one. So that are, as I already mentioned, that we are, first of all, the assumption is that whatever the abrasive particles that we are using, they are basically in a spherical in nature, okay. So generally they are like this random in shape, okay, random in shape, but we are considering the average diameter of that, but overall we are considering that into the spherical form, okay. So that is spherical in nature, and that is in the range of 10 to 50 micron, 50, okay. Why it is 10 to 50 micron? Because if we talk about the alumina, then this is in the, this is available in the range of 10 micron, 20 micron, and 50 microns, Okay, this is available in this range. Okay, now if we talk about or like other also, like silicon carbide is also we can use as a abrasive particle, which is little bit harder than the alumina. So that is in the that is available in the range of 20 and 40 microns. Okay, and similarly like glass beads is also available, but these are in microns. These are in micrometers or microns we can say, but glass beads diameter is generally like zero point 0.2 mm. Okay, so that is like we can say in micrometers, if we are comparing with the mm, that mm is large size. Okay, so that's why we are keeping this avoiding this one, but if there is a need we can use this one as well. Okay, so but this has a higher strength than these two. Okay, please keep in mind that one. So these are the abrasive particles. So here basically, as I mentioned, that 10 to 50 micron, that is due to the average of all these things, like 10, 20, 50 is available here, 40, 20 and 40 is available. So on an average, like we can say like 10 to 50 50 microns diameter we can use. Okay, next is the carrier gas. As I mentioned, that carrier gas, like simply air is available, so that we can use, or apart from this, CO2 and the N2 can also be used for this purpose. Okay guys, the pressure that we are maintaining, that is in the range of 2 to 10 bar of the air compressor. And the average density, this density is basically the average density, that is in that is 1.3 kg per meter cube. The reason is, like if we talk about the air, then air generally have the density of like 1.25, okay, kg per meter cube, or 1.215 kg per meter cube. And similarly, if we talk about the CO2, then that is in the range of the density of that is in the range of 1.95 or 915 kg per meter cube. So like on an average we are just taking, and similarly in the range of N2 as well. So on an average we are taking density that is in the range of 1.3 kg per meter cube. Okay guys, next is the abrasive jet, that which is the combination of abrasive particle and the jet gas we are using, the combination of these two. Okay, so the velocity that we are maintaining, that is above the 150 meter per second, and that is in the range of, if we are talking about the range, then this is in the range of 150 to 300 meter per second. Okay, the standoff distance, as I mentioned, the standoff distance, which is very important criteria, and we also can say like NTD, nozzle tip distance. Okay, so that is in the range of 0.5 to 5 mm. Okay, next is the like mixing ratio. I will tell after this impingement angle. This impingement angle, we have already discussed that we just have to rotate this nozzle, and this should be like this angle is decided generally at the optimum values, that when we are getting the optimum values of material removal rate. So this is in the range of 60 to 90 degree. Okay, next is like the mixing ratio. Okay, so mixing ratio is very important criteria for the abrasive jet machining. It is defined the volume of, it is defined, it is basically the ratio, and it defined the volume of volume flow rate of abrasives or abrasive particles. Okay, and upon volume flow rate of gas or air we can say. Okay, so this is very important criteria, that how much amount, if we are mixing ratio is given, that mixing ratio means in the mixture we are that mixing air, abrasive particles and the gas. So what is the mixing ratio? Okay, so that we have to keep in mind, that how much volume of the abrasive particles that we are using upon the volume of the gases, volume flow rate of the gases that we are using. So please keep in mind, do not reciprocate it. Okay, उल्टा मत कर देना इसको, ठीक है, उल्टा मत करना इसको, गलत हो जाएगा. Next is the nozzle. Okay, the nozzle that we are using, so that is generally made up of the tungsten carbide, that is WC, and the sapphire, because it has a very high hardness, as well as it has a very high wear resistance at very high temperature. Okay, so generally like for the abrasive jet machining only we are using this one. If we are using the abrasive water jet machining, तो फिर हमें इतना hard use करने की जरूरत नहीं है. We can use the softer as well, because in that case basically water is worked as a lubricant. Okay, so for that abrasive water jet machining we can use the softer material of the nozzle as well. Okay, but here the abrasive particle which is moving with very high velocity along with the gases, so we have to keep in mind, because these abrasive particles is there, so definitely it is it will collide. Definitely when it is moving inside, when it is moving inside, no doubt it's not like it should move straight in a straight line. It should definitely collide here as well, or the adjustable boundaries or the boundaries of this nozzle. So there will be a wear as well. Okay, so please keep in mind. So that only we are using this harder material, okay, which has a very high wear resistance, and the diameter that we are using in the range of 0.2 to 0.8 mm, that I already mentioned, guys. Okay, that this diameter adjustable boundaries we are using. So if we have to reduce the diameter, we can move them inside, and if we have to increase this diameter, we can move up to like up to the final boundaries, up to this one. Okay, so this can be vary from 0.2 to 0.8 mm. Okay, guys. So till now, guys, if you have any doubt, you can ask me. Then we'll go for the material removal rate. I will discuss this part today, and next modeling will start tomorrow. Okay, in the next class. So if you have any doubt, you can ask me, guys. I'm just giving you 1 minute. By the way, guys, I 41 students are present today. Okay, that's good that maximum areas internet is working. Okay, for few students only we have to manage, so there will be no issue. Okay, guys, so if everything is clear, then let's move to the next one. That is modeling of material removal rate. Okay, so modeling of material removal rate, that we model the same material removal rate in the EDM process as well. That what is the material removal, actually the material removal mechanism is there, and how this material is removed. So guys, please concentrate that this process AJM, this abrasive jet machining process, is applicable for both type of the material. Both type means either it can be a ductile material or it can be a brittle material. Okay, ductile material which is softer in nature, which is soft, and brittle material which is hard. Okay, so let's discuss first with the brittle material. That this is the abrasive particle. Okay, and generally the size of this abrasive particle is defined by the diameter. Okay, so if this is the like center, okay, then we are just assuming that this is the diameter of this one. And as I mentioned in the beginning, that here we are defining this abrasive particle by the grit. Okay, so this is a grit. Okay, and this diameter is represented by the d small z in subscription. Okay, so in subscript it's g. Okay, so this is dg. Okay, this is the diameter of the grit, which is defined that 10 micron. If we are talking about the alumina, then 10 micron. So that is basically the diameter of this, okay, grit. So this abrasive grit is initially it's like this is the workpiece. Okay, this is the workpiece, and this is the abrasive particle. Okay, abrasive grit we can say, as it will impinge over the workpiece surface. So when it will impinge over the workpiece surface, there are two cases. First case is which is related with the brittle material. Second case which is related with the ductile material. So first we are talking about the brittle material, guys. Okay, which is a harder material. So I'm just considering that when this abrasive particle, I'm just talking about here with the single abrasive particle. So when this single abrasive particle will impinge over the workpiece surface, it will be like there are two possibilities. First is like just throw a ball on the wall. Okay, guys, just throw a ball on the wall. So there will be like there will be no removal of the material. Okay, but as you are continuously hitting the ball on the wall or a particular point, then after some time there will be a crack initiation. Okay, guys, so I'm talking about the leather ball or a cork ball. Okay, guys, so when you will hit this cork ball or leather ball on the wall, continuously hitting on a particular, on a single point, not on complete wall. Okay, single point when you will hit, after some time the crack will initiate. This crack is initiated due to the removal of the material, due to the internal stresses, which is we are calling it as a residual stresses. They become basically uh, less in quantity, because whatever the force that you are impact force is there. So because of that impactness, this will become loose. The bond of these molecules inside the material will become loose. So now it is crack is initiated. Okay, and as you will hit continuously, this crack is propagated. it will propagate and there will be a removal of the material, okay, from the wall. So similar example is here. These are the abrasive particles. As we are impinging this abrasive particle over the workpiece surface, first either it can like just collide with this surface, okay, and they it will, as it has a very high velocity, so it will move in any direction at 360 degree. Or like what it can be, another possibility is it can move little bit inside, that will remove the material, and then it will move in any direction. There are two possibilities. First is it will hit, if it has the sufficient strength, then if it will hit the surface, workpiece surface, and it will move in any direction. Because simply like when I'm like this is simply kind of rubber, okay, and when I'm impinging over the workpiece surface, as it is impacting, then it is moving in any direction, okay guys. So this is just a rubber, so as it is uh, hitting the workpiece surface and just going in any direction, like similarly abrasive particle will happen. They will impinge, they will come in contact with the workpiece surface, and they will move in any direction. Or there is a possibility that if has a very high strength, as we are using very high velocity as well along with that, so it will impinge inside the workpiece surface, because some of the indentation it will create, and that will remove the area. So this possibility we are considering, okay, that we are using this abrasive particles which has a very high strength, as well as we are using very high velocity, abrasive jet velocity, that is greater than 150 meter per second. So definitely it will impinge over the workpiece surface. So still I am considering the example of the brittle material only, guys. Okay, so now let's come to the brittle material, to this figure. Like when it has been impinged over the workpiece surface, that time we are considering. Now, as it has been impinged over the workpiece surface and it is a brittle material, this workpiece is the brittle material, then like initially it is impinged over this area. Sorry. It is a little bit like this, okay, circular. So when it is impinging over the workpiece surface, it is like this, okay. And as it has a very high velocity, so definitely there will be an impingement, or we can say there will be an indentation, okay. So like this is the center point. This is we are considering that this is the center point, and is we are considering that this is the spherical in nature. So this ball, when it will hit the workpiece surface, it will try to cover some specific area from the workpiece, okay. Now when you will see from the top view, then this area is covered by this impingement, or by this specific uh, we can say abrasive particle. So if this is the center, then from this center, this is the center, from this center basically we are considering that this radius is r. This radius is basically the small r, or we can say rg as well, but I'm just writing small r only. Why I'm writing this r? As I said, that when you will see from the top view, is the spherical, this abrasive particle which is spherical in nature, it will impinge the workpiece surface and they will basically try to remove the material. So when this ball is hitting the workpiece surface and it is moving in any direction, that after that when you will see the workpiece, it will be like this kind of shape is formed, a semi-spherical kind of shape is formed. Now why I'm calling it as a semi-spherical, the reason is like whatever the this was the center and this much radius is covered. So when you will see this one, then this will be like from this one, this point to this one, this is also small r, and from this center to this one, this is also small r, okay. So that's why when this is small r, then it should be looks like a hemisphere. So this is the material removal mechanism. Alam Shafi. Okay, so this is the material removal process, or the how the material is removed exactly in the brittle material. Okay, guys. Next is for the ductile material. Okay, so this is for the hard material. Next, consider the for the ductile material. So ductile material, if you are talking about the ductile material, then just take an example of rubber. Okay, so rubber is like I'm just taking this rubber. Okay, it's just very simple. So when the abrasive particle is impinged over the workpiece surface, or it's like my nail is there, so I'm impinging over the workpiece surface. So it has basically the energy to absorb the load. Okay, because it has a very high toughness. softer material has a high toughness than the brittle material. So it has the toughness. It means that whatever the load I am impinging over the workpiece surface, it has the capacity, it has the energy to absorb that load. It is no doubt it will absorb the load, but as this abrasive particle is very high strength and very high velocity, so it is impinging over the workpiece surface. It is not like falling. Okay, so it is impinging over the workpiece surface. So whatever the mechanism that was happening in the brittle material, the same mechanism, as it is ball is falling and they will basically remove the material from the workpiece, the same mechanism will happen here as well. But as it is a ductile material, so whatever the surface, bottom surface that will come in contact with this abrasive particle, they will try to show some loading. They will try to show some load. What it mean is the surface will not be exactly what the surface is forming in the brittle material. It should be like this. Exactly, the abrasive particle, this is the ductile case, so exactly the abrasive particle came in contact with this much area, but only this much amount of the material is removed from the workpiece area. This much amount, only this much amount of the material is removed from the workpiece area, not this one, by the way, not this one. This area is not removed, but it doesn't mean that workpiece, this abrasive particle came in contact only up to this much. No, abrasive particle was came in contact with up to this one. So we are defining this by the delta, and this delta is basically the maximum indentation. This delta, or we can also write like maximum. So this is the maximum indentation. This is the maximum indentation. Okay, so that is the up to that there is an impingement. But now let's see how much amount of the material is removed. So now we are assuming that only this much amount of the material is removed. This red color, please look at guys, this is red color only. Okay, so same like here, this is the center I am considering. Here this is the center I am considering, this green one, and up to this one there is a radius is there, a specific some radius is there, but now we cannot consider that equal to small r. The reason is here exactly not this, it is in spherical in nature, but exactly we cannot say it's which nature it is. Okay, because we cannot say which nature is it, because this material has become like this. Okay, so we cannot say it's hemisphere or not, but if you will see from the top view, then top view it will be looks like a circular only. From the top view it is looks like a circle. Okay, so when if I am taking this as a center, then this some radius will be there. Now how much radius will be there? This will be, we are just assuming that whatever the indentation is there, that is, we are just assuming that this indentation is delta. Exactly, it is delta maximum, but as I said that some amount of the material is shocked by the workpiece, so that will be that will not move from the workpiece, or that should not be removed from the workpiece. Okay, so this is, we are just calling it as a delta, that is the indentation or the radius we can say. If we are calling it as a radius, then this is the radius. Okay, and this is radius is like this is of this circle. Okay, which will be visible from the top view. By the way, like from, if you will see from this side, by the way, like we can say that from this center this distance will also be delta, but sometimes this distance will not be delta, it can be something else. Okay, so that's why we cannot consider that for ductile material it will be a semi-sphere, we cannot say. But so yeah, for the ductile material it should not be a semi-sphere, but for the brittle material we can say it should be a semi-sphere. Okay guys, so let's discuss what the assumptions that we have to consider while the modeling of MRR. The abrasive spherical in shape and rigid, that particle are characterized by the grid diameter that we have already discussed guys. The kinetic energy of the particle is fully utilized in the removing of the material. This guys I will tell you most probably in the next class. Okay, the exact meaning of this one, but for the time being just consider that whatever the kinetic energy of this abrasive particle which is impinging over the workpiece surface, it is completely utilized to remove the material. Okay guys, for the brittle material, consider to fail due to the brittle fracture. okay, and the fracture volume is considered to be semi-sphere for the brittle one. Okay, for the ductile material, removal volume is assumed to be equal to the indentation volume to particulate impact. So that basically we will see in the next lecture. Okay, guys. So up to this, I'm just stopping for today's class. Guys, if you have any doubt, you can ask me. By the time being, I'm just taking your attendance. Okay, guys. So if you do not have any doubt, then I think we should end this class. Okay. So